Picking back up with example 2 in our lesson 12.2, we have a new infinite series, much simpler looking. The formula is -1 to the n minus 1. S sub 1 would simply be the first term. Let n equal 1. 1 minus 1 is 0. -1 raised up to that 0 power is a 1. So the first term would be a 1. Even in the sequence, there's just one term to add up, that is. S sub 2 means add up the first two terms generated by that sequence, really. We already saw that the first term was a 1. What's the second term? Well, let n equal 2 up here, and we'd get 2 minus 1 is 1. -1 to the first power is -1. And if you add those together, you quickly see you get 0. If we took S sub 3, that says add up the first three terms generated. We just saw a moment ago that the first term was 1, the second term was -1. The big question, of course, is what is the third term? If we were to let n equal 3, 3 minus 1 up on top, that exponent is a 2. -1 to the second power is another 1. And of course, we can add this up. You can see quickly you just get a 1. Keep going, S sub 4. Hopefully you can see a pattern emerging. You're going to say, well, add up the first first four terms. We already know what the first three would be. What's the fourth term? Well, let n equal 4. 4 minus 1 is a 3. -1 to the third power is actually -1. Add all these up, you can see you're back to 0. How about S sub 5? Well, that means you'll take your first 5 terms and add them up. We already know what the first 4 terms look like. That's recopying. The fifth term, 5 minus 1 is 4. -1 to the fourth power is another +1. Here you go. You might not be too surprised to guess that S sub 6 is going to go back to 0. It will. Let's see what's happening. It means add up your first 6 terms. Here were your 5, the first 5. What exactly is your sixth term, though? Let n equal 6. 6 minus 1 is a 5. -1 to the fifth is another -1. And very clearly you can see you get 0. So look at these partial sums. You'll go from a 1 to a 0 to a 1 to a 0, from a 1 to a 0. And obviously we're not going to do a partial fraction here. But S sub n, you might not be too surprised. You're just going to have two possibilities. You're going to have 1 or 0. You're going to have 1 if n is odd. You're going to have 0 if n is even. So the big question is, would we get convergence or divergence? Clearly this is divergence. You're oscillating between a sum of 1 and 0. The limit as n goes to infinity of S sub n, there's no way you're going to arrive at one distinct number, either 1 or 0. So this doesn't exist. Therefore this series, notice I'm not even putting bounds in. We'll say this diverges. Number 3 is super, super, super important. This is one of the most famous series of all. By the way, we will reference this series countless times in this chapter. This series is known, 1 over n, adding up from n equals 1 to infinity. It's known as the Harmonic Series. It will be used repeatedly in comparisons with other series that we're going to do down the road. We need to know as a statement of fact that that series actually diverges. And to help you see that, I'm going to do a little bit of a proof right now. Let's just examine what's happening as we would look at this series. If I gave you 1 over n, and let's just expand and write out what this series would look like. The first term would, of course, be a 1. the second term, letting n equal 2, you'd get 1/2. Then you'd get the third term is 1/3, fourth term is 1/4, a fifth term, and you get the idea. We'd get 1/6 plus 1/7 plus 1/8, and so on. And this is going to go on really forever. Now, the big question is, how in the world can we see that this actually is going to diverge? Well, let's set up another series to compare. Let's say consider a new series. Consider that I had 1 plus 1/2, but now I'm going to look at 1/3 and 1/4. And tell you what, I'm going to know that 1/3 is actually larger than 1/4. 1/3, of course, is larger than 1/4. What I'm going to do is make a new series over here and replace 1/3 with 1/4. So I'm comparing this sum up above, and I'm making a new series right here, and I'm changing a few things. I'm saying, look, instead of adding a 1/3, let's just say we replace that with something smaller, 1/4. The larger a denominator is, obviously, the smaller that fraction is. In a very similar way, as I compare 1/5 to a 1/8, how about I look at all of these? This 1/5 I'm going to replace with 1/8, and the 1/6 I replace with 1/8, and the 1/7 I replace with 1/8. And by the way, if I kept going, I could now go by powers of 2. The next grouping I would create would be 1/16, actually, if I really wanted to do that, extending it. Why am I looking at this new series? Well, let's consider that 1/4 plus 1/4 is 2/4, and that would go to 1/2. 1/8 plus 1/8 plus 1/8 plus 1/8 would be 4/8. This would also be 1/2. And if I grouped all these 16ths right here, comparing all the way up, you could eventually see that you'd get 8 of them. And another grouping right here would be 1/2. So what I'm getting at is I'm saying let's add 1 and then a half and then another half and another half and go on forever. Now, if I just gave you that, 1 plus a half plus a half plus a half plus a half forever, we can say the new series diverges. The new series very clearly is going to, add up to something infinite as we continue to add forever. Imagine if I just said keep adding a 1 and a 1 and a 1. Well, a half and a half is a 1. So, we're getting this, massive sum as we go on towards infinity. But, and this is the big key, this series is larger. It's even bigger. Why? Because term by term, like we said, the 1/3 here was bigger than the 1/4. Right here, 1/5 is bigger than 1/8. 1/6 is bigger than 1/8. So we're doing this proof saying, look, if the new series creation that we created, if that's heading off towards an infinite sum, that means that this series, the harmonic series, diverges. This is a statement of fact. You're not going to be asked to recreate this proof, but it will show up a lot. And you want to know for a statement of fact that the harmonic series will diverge. Very, very, very important piece of information. With that in mind, we need to also take a look at another exceptionally important series. Just as I said before, the harmonic series will be referenced countless times in this unit. So will the geometric series. The geometric series, and thank goodness this is something that you studied in AMA as well. It's a geometric sequence that gets added up. Term by term, we're just multiplying by a common ratio. We're multiplying by r. So it's this infinite sum where each term in the sequence that we're adding up is just being multiplied by a common ratio r. We're going to see that your geometric series will converge if your common ratio, what you're multiplying by, your r, is less than 1 in absolute value. We said before that this is really meaning that r is between -1 and +1. If that's the case, if that common ratio that you're multiplying by is between -1 and 1, then make sure you're memorizing this as a fact. That infinite sum will be the first term divided by 1 minus the common ratio. Sometimes you'll even see some textbooks write a little infinity down there saying, add that up forever. You're going to arrive at first term all over 1 minus r. By way of comparison, if that common ratio in absolute value is bigger than or equal to 1, that series will diverge. So let's take a look at what's happening here. We've got example 4, and we can say, well, here's your first term. It's 4/3, but the big question is, how do I get to each successive term? What am I really multiplying by? And I hope you can see very quickly, going from 4/3 to 4/9, only the denominator changed, and it was multiplied by 3. So you would quickly see that r is equal to 1/3. Now you're going to know that the absolute value of r is less than 1. That means that your geometric series, because each successive term is found by multiplying by 1/3 on the previous term, we're going to add that up forever. We're going to say, you know what? This is going to converge to a sub 1 all over 1 minus r. That's going to be 4/3 over 1 minus the r value of 1/3. So take a look at this. We'll get 4/3. 1 minus 1/3 is really 2/3. And here's some clever canceling. You can just cancel out your denominators. 4 divided by 2 is 2. This series converges. It converges to 2. So this is, again, something that we want to recognize. If we see that multiplication going term by term by term, look at that multiplication factor. We call that r. If r is less than 1 in absolute value, this is the formula you're going to use. It even shows up regularly on the AP exam. By the way, even this formula is something that you did see last year in your pre-calculus class, Accelerated Math Analysis. Okay, we're going to wrap up now with really just cleaning up a few things. Here's a theorem. If a series is convergent, then the limit of the formula, the nth term of the sequence, will go to 0. I'll be honest with you, we don't usually use this theorem directly, hardly at all. What we do use is its contrapositive. And the contrapositive, this is something you would have learned back in geometry, says if P implies Q, if P, then Q, if that's a true statement, and by the way, here's your P statement and here's your Q statement right here. If P, then Q, then the contrapositive is not Q implies not P. This is always true. If a statement is true, its contrapositive must also be true. So this theorem is definitely true. So let's do not Q. Not Q means if the limit as n goes to infinity of a sub n is not 0, then not P, then that series is not convergent. That means that a sub n diverges This is the nth term test.